Okay, today we are going to learn about energy. And we're going to learn how it interacts and how it changes from type to type and all that kind of stuff. Hopefully you have a little review sheet or a note sheet in front of you. If not, look onto your neighbor or find one when you get back. But the important definition, energy is defined as the ability to do work. So if we have energy, we can do work. If we have done work, we have changed the amount of energy that's in something else. Energy comes in several different types of forms. Some energy is used right away, and some energy is stored up for later. The stuff that's stored up for later we call potential energy because it has the potential to do work later. So potential energy can do work at a later time. Now, there are three types of potential energy that are very common to us. The first one is called chemical potential energy. And with chemical potential energy, this is energy that's stored in chemical bonds. And so ideally you learned in biology class that there's an energy currency of the cell called ADP or ATP. And when they break off a phosphate, it turns into ADP. And that breaking off of the phosphate, that breaking of the bond releases energy. And that energy is used for different cellular purposes there. So ATP, ADP, that's one of the things that you learned in biology. Another thing you should have learned in both biology and health class is that if you put more energy into your body in the form of food than you use up in the course of the day, then your body stores that as potential energy that we call fat. So that's an example of chemical potential energy. Ideally in chemistry class, you learn that chemical potential energy is things like gasoline in your car. Anytime that you break a bond, then you release energy, and anytime you form a bond, you absorb energy. If the reactants are breaking up more than the products are forming, then there's extra energy left over, and that energy is given off as heat, and we have what's called an exothermic reaction. On the other hand, if the products absorb more than the reactants broke up, then we have a net negative, and so it actually gets colder. We call that an endothermic reaction. So ideally, you've heard about these things before. That's chemical potential energy. The second type of common potential energy is called nuclear potential energy. And nuclear potential energy is where energy is actually stored up in mass. You can, in fact, turn mass into energy in certain situations. Actually, in a chemical reaction, you do turn super duper duper tiny amounts of energy, of mass into energy. But you see it more in the major chemical reactions where actual new things are formed. Like if you're changing from hydrogen or from helium, hydrogen into helium. If you're changing from hydrogen into helium, if you add up the mass of the neutrons and the mass of the protons that are stuck together in the nucleus, the mass in the helium is actually smaller than what you would expect it to be. We have lost some mass, and that mass turns into energy, in this case in the form of bond energy that holds those nuclei together. You've probably heard of this equation before and never knew what it was for. But when you see that equation, E equals mc squared, everybody knows that's Einstein's equation. They know it has something to do with something, and it's very famous, but what does it have to do with? This is really our nuclear potential energy equation. The E stands for energy, the M stands for mass, C stands for the speed of light. But the mass here, when we have some mass that disappears, that mass turns into that bonding energy, the binding energy that's happening in the nucleus. And so that's just an equation that explains how much energy we expect when mass seems to disappear. So we've got that one. The third type of potential energy that's important and very common is gravitational potential energy. So gravitational potential energy, of course, deals with gravity, and anything that has height has the potential to fall. So if we have height, we can potentially fall, and if we do fall, then that falling energy can do work. And so gravitational energy is basically energy stored up in height. When I lift something up, I do work on that. I put some potential energy in it, in this case, the gravitational potential energy. And that could easily be dropped, and then if it drops, it does work on something. So if I drop Bob on your foot, it would do work on your foot. If I drop it on an aluminum can, it would crush that can and do work on that can. So the amount of work done is dependent on how much energy is in that thing. So in this class, when we're talking about potential energy, we're talking about the gravitational potential energy, not the chemical and nuclear. Although they are interesting, they're not what we're talking about here. So if you just hear potential energy without anything in front of it, it's gravitational potential energy. So our formula to calculate gravitational potential energy is really easy. It's just mgh, mass times gravity times height. Well, mass times gravity together, of course, is weight, and weight is measured in newtons, and height is measured in meters. So here we have a Newton meter, which is, of course, a joule. So it's not really surprising that joule, that was the unit of work, is also the unit of energy, because energy is the ability to do work, and so work changes the amount of energy we have. So they're talking about the same thing, the same concept, so they have the same unit. So that's not a big deal. So if we have a bowling ball that falls off a table, well, how much work can be done on your foot if it falls? Well, to find that out, all we have to do is say, well, how much work can be done on me is equal to the amount of energy it has. If energy is the ability to do work, then I can't do more work than the amount of energy I have. So in this case, the amount of energy I have is dependent on the mass, the gravity, the height. So if we have the ball, and if this bowling ball is, we'll put it up here. So if we put this ball up at a height, then it can potentially fall, of course. So if it's going to fall, we want to know, well, how much energy does it have? Well, again, we just say PE equals mgh. So the mass here was, it was an 8.732 kilogram ball, and G is, of course, G 9.81, and then the H is 1.23. So if I multiply these three together, I find how much energy I have. So if I take 8.732 times 9.81 times 1.23, I find that I have a total of 105 joules of energy. So if there's 105 joules of energy in there because of its height, then the most amount of work that this ball can do when it falls is 105 joules worth of energy. And 105 joules worth of work. So that's all we got. Second question was, how fast is the ball going to travel when it crushes your foot? Well, to understand this, we need to know more about immediate energy. One type of immediate energy is energy of motion. Energy of motion is called kinetic energy. So energy of motion is called kinetic energy. Now, kinetic is a nice fancy word that just means movement. So anything that moves is kinetic. So energy of motion is kinetic energy. Now here we're dealing with how fast it is and how big it is. So the kinetic energy formula turns out to be mv squared over 2. Now, what happens is, if we look at this energy, we will find that energy is very similar to what momentum was. In momentum, in a collision, the momentum didn't magically appear, it didn't magically disappear. It could shift from one object to another, but the total amount of momentum was still there before and after. Energy is the same way. Energy is conserved. What we have found out is that you can't make energy, you can't get magic energy from nowhere, and energy doesn't magically disappear. This is what we have found over and over and over. When you do careful studies, the energy always goes somewhere. So, if I take Bob, for instance, and I put Bob right over your foot. So, if your foot's here, and I put Bob just a little tiny bit over the top of it, you're going to say, fine, go ahead, drop him, I don't care. However, if I bring Bob up a little higher, you're starting to think, this isn't such a good idea. And the higher I bring up Bob, you're starting thinking, this is going to really, really hurt. Because Bob still has the same mass, but since he has more height, he's got more of that potential energy. So that potential energy will turn into kinetic energy as it falls. Because as it falls, what's going to happen is the height is getting smaller, but the speed is getting faster. And so the kinetic is getting bigger, the potential is getting smaller. What happens is they end up equaling each other. So the amount of work that we said that this could do, the 105 joules is the total potential it has. That 105 joules will turn into kinetic as it's falling and is about to hit your foot. Of course, if we have a golf ball instead, I can put the golf ball super high over your foot, and you don't care if I drop that one under your foot because it's going to have much less kinetic energy. It's still going to go the same speed the ball would if they fall from the same height, but of course, its mass is so much smaller that you don't care, and you would like that a lot more. So getting back to our balls, if I took this golf ball and the golf ball was at a very high height and I dropped this golf ball, of course it's going to accelerate down, it's going to hit the floor, and it's going to bounce back. But it's not going to bounce back to the same height it took off from. It's always going to bounce a little lower and a little lower and a little lower and a little lower, 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 lower. Why does it get smaller all the time? Doesn't that seem to say that some energy is lost? It doesn't say that the energy is lost. It says the energy changes to a different form. Now, originally up here, the only kind of energy that it has when it's at the highest point is potential energy, because at this point, it's not moving. So all it has is height. But as it's falling, what's happening is I'm losing my height, but I'm gaining speed. So down here, I have velocity. So that means I'm going to have kinetic energy. Well, the amount of potential I had at the top just turned into the kinetic I had at the bottom. So we get this equation that says the change in potential equals the change in kinetic equals the change in work. So what this equation tells me is if I lose potential energy, I either gain kinetic energy because it got faster, or I did some work. Like if I dropped the ball on top of a nail and it was driven into the piece of wood, I did some work there. I applied a force over a distance. I got some work done. If I change my kinetic energy, if my kinetic energy gets smaller, that either means I gain some potential energy. If I'm getting slower, I either went up higher or I did some work. On the other hand, if I do some work, I either change the potential energy or I change the kinetic energy. For instance, if Bob is down here on the floor, if I want to do some work on him, I'm either going to do work on him upwards, which means I increased his potential energy, or I'm going to do work on him sideways, which means I increased his kinetic energy. So if I apply a force over a distance this way, he got more potential energy, but if I apply a force over a distance this way, I increased his speed and changed his kinetic energy. So that's what we're looking at, is that these are interconnected. It does not say the potential energy equals the kinetic energy. It says if I lose some of one type of energy, I must be gaining another type of energy. And of course, this can occur not in just these types of energy, but any type of energy. So for instance, if we have the golf ball, if the golf ball is way high, and again, going back to I'm dropping the golf ball and it's going to bounce lower and lower and lower every time I bounce it. If I start off up here, again, it's all potential. Right before it hits the ground, it's all kinetic, but then it does hit the ground. When it hits the ground, two things happen. Number one, you hear it hit the ground. If you hear it hit the ground, then some of that energy turned into sound energy. It needed to do some work on your eardrums. It moved some air around in the room. In doing that, that takes some energy away from the ball. So the ball cannot bounce up to the same height it was before. It bounces up to a lower height. So if it bounces up to a lower height, we lost some height, which means that energy turned into another form, in this case sound. It also turns into heat. And so there's a little bit of sound, a little bit of heat that's taken out of here. And so it bounces a little bit lower every single time. But this is what we're talking about here. So if the ball is falling, going way back to the problem we started a long time ago, we had Bob sitting on a table. If he was sitting on a table and we found out how much potential energy he had, that was 105 joules, he's going to fall. Now, when he falls, it's going to turn into kinetic energy. So how much kinetic energy is it going to turn into? Again, with that equation I just erased, it said the potential equals the kinetic equals the work, the change in all of those. And so what we're going to do is you never use all three parts of that. You only use two. In this case, we're going to say the loss of potential equals the gain in kinetic. Well, if I know my potential energy equals mgh, I know my kinetic energy equals mv squared over 2, I notice that, hey, look, the m's are going to cancel out. If I want to know how fast it's going, all I got to do is bring the 2 up here, and then to get rid of this, I need to square root. So after making that prettier, we say, hey, the square root of 2gh is equal to v. And that lets me know that, hey, if I lose potential and I gain kinetic again, this is going to happen before you hit the floor, all of that potential just turned into kinetic. Once I hit the floor, it also turned into heat and sound, and so I don't pop up to the same amount I had before. But here, I'm just going to say, hey, how fast is it going right before it hits my foot? It's going to go 2 times 9.81 times the height of 1.23. So, if we plug that into the calculator, 2 times 9.81 times 1.23, and we find out that he was going a whopping 4.91 meters per second right when it hit your foot. Definite ouch. You're going to limp. So, what happens is when I lose one type of energy, I'm gaining another type of energy, or I'm doing some work. And so I see this happening all the time. If we switch to our next problem, we have Mark has a 742 kilogram car going 14.4 meters per second down the street when it runs out of gas. If we have 742 kilograms, obviously that's our mass. He's going 14.4 meters per second. That's obviously a velocity. If I run out of gas, I haven't really run out of energy, though. I've run out of the chemical potential energy. I'm not going to get faster, but I still am going 14.4 meters per second, so I still have kinetic energy. So the first thing I'm asking is, how much energy does this car still have? So what I'm really saying is, how much kinetic energy do I still have? Well, the kinetic energy equation, again, is super simple. It's just mv squared over 2. Well, gee, what do you know? I know both m and v. So I have 742 times 14.4 squared over 2. And if we multiply that out, we get 76,900 joules. And you're saying, wow, that number is ginormous. Yes, when we talked about Bob falling on your foot and you said that you wouldn't want that to happen, that was only 105 joules. Here we have 76,000 joules. Why is it so much more? Well, it's a car. It's much, much bigger mass. It's also a bigger velocity. So you really don't want to be in front of a car. That really, 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 really hurts. Now, the second question said, how far up a hill can he coast? Well, if the car is cruising along and it's got some speed to it, it's going to cruise along, but once it hits a hill, it's going to go up the hill, but it can only go up the hill until the kinetic energy all turns into potential. Once the amount of kinetic energy that it has turns into potential, then I can't go up any higher. And so at that point, it would roll back down. So I can either plug in this number as my potential, or I can just go back to that equation again and say the potential energy that it gains comes from the fact that it's going to lose that kinetic energy. So again, I can say mv squared over 2, sorry, that was the kinetic side, equals the potential of mgh. So again, this side is this and this side is this. I wrote it backwards. If I'm looking for how high it goes, I have this. And so the g is going to go from the top to the bottom. So that's going to be g down here, and the m cancels out on both sides. And so to find my height, it's just going to be v squared over 2g. Well, the v squared, we already figured out the car was going 14.4 before we started going up the hill. And then we're going to just have this. So if you use fraction mode on your calculator, make it look just like that. If you're not using fraction mode on your calculator, you want to go 14.4 squared divided by 2 and divided by 9.81. So either way, if we do that, let's see, squared divided by 2 divided by 9.81, we end up with, it can go 10.6 meters up the hill no más. Once I get to that point, if I have run out of kinetic energy, so I'm going to stop, and then I would roll back down the hill. And so that's all the higher I can get. Our third question, we had Maxine swinging on her swing. So if we have a swing set, this is a great example of what happens with kinetic and potential energy transformations. Love my beautiful drawing, right? So at the top here at point A, she has a certain amount of height, and then she's going to swing over here. Now, normally, if you're swinging, you're going to swing all the way from here all the way up to here. So you're going to swing through this entire arc, and you're going to swing to the same height. But what I'm saying is, what would happen if we stop her right here? Obviously, she's not going to really stop, but if we just instantaneously look at the motion when she's right here, what's going to happen is we find out that up at this point, she has all potential. Up at this point, she has all potential. We stop when we go up to this point, then we stop again when we're up at this point. The fastest speed is going to be down here where it's all kinetic. So here where it's all kinetic, we have run out of height. Our swing can't go any lower. So we've run out of potential, and here we have kinetic. So here we're going to have the most speed down at the bottom, and up here we're going to have the most height. So here, if we're at point B, what's going to happen is, at A, she had all potential energy. At the bottom, she had all kinetic, but at point B, she's going to have a little bit of both. So here she's going to have both kinetic and potential. Well, if I gave you this height, and I gave you this height, and we're trying to find out, well, which height am I going to use? I don't use either one of these heights. What I have to do is figure out how much height did she lose. In the previous two examples, what happened is the bowling ball, when it fell off the table, it fell all the way to the ground, so it lost 100% of its potential to turn into kinetic. In the car was rolling, and it went up the hill until it came to a complete stop. So it went up until all the kinetic turned into potential. But here, only some of the potential has turned into kinetic. So I'm really worried about how much of a height change did I have here. That's going to tell me what I'm going to do. So I'm still going to say the mgh, the potential, equals the mv squared over 2. The kinetic, the potential loss, equals the kinetic gain. But the height I'm going to use here is going to be the change in height between these two. And I gave you 8.42 was this height. And this height over here was 5.82 meters. So yes, I realize this is the biggest swing in history, but we're just playing here. So the change in height here, if I subtract those two, we find out that she drops 2.6 from point A to point B. The fact that she went lower than that and came back up doesn't really matter because she lost some of that but then gained some of that back. So right there at point B, she has lost 2.6 meters. So that's going to be the height that we plug in. And again, the m's go away, the 2 moves up to here, and we square root to get rid of that. And so we're just going to have the square root of 2 times 9.81 times the height change of 2.6. And we find that that is 7.14 meters per second. So that would be how fast she's going at part B. Now, the big question is, how in the world did she get up to point A in the first place? You don't start off in your swings up there. So the only reason she got up there is because somebody, it might have been her, did some work on her. So it might have been her swinging back and forth and leaning back and forth a bunch of times, or it could have been her dad behind her giving her some shoves. Either way, somebody did work. Somebody applied forces over distances and gave her energy. So the only reason she has energy here is because somebody did some work on her. Now, if somebody did work on her and change that energy, then all we want to know now is, well, how much work did they do? Well, how much energy does she have now? That's how much work was done. So up there, she has a certain amount of potential energy. That's just mgh. So her 42 kilogram mass at 9.81 is up 8.42 meters. And so if we've got this worked out, we find out that it was 3,470 joules to get it all the way up that high. So Dad had to do a lot of work doing all that pushing. Now, the question is, where did this energy come from? Well, it came from Dad's muscles. Well, where did Dad's muscles get the energy from? From the cheeseburger he ate at lunch. Where did the cheeseburger get its energy from? From the cow. Well, where did the cow get its energy from? From the sun. Well, sorry, from the grass that the cow ate, and the grass, of course, got its energy from the sun. If we trace our energy changes back far enough, we almost always end up at the sun. And so the sun is constantly giving us energy. Now, the reason we're not getting hotter and hotter and hotter and hotter is because the sun's over here giving energy to us, but as we spin around and we're over here on the dark side, the energy is coming off from us. So here we're soaking in energy, here we're getting out energy, and gee, what do you know? We're in equilibrium all the time. So we soak up some, we give off some, overall the planet stays pretty much the same. Now, different parts of the planet change because in summer we have more light, we have more hours of light than we have hours of darkness, so the planet keeps getting hotter and hotter and hotter for us. But then in winter, we have less hours of light and more hours of darkness, and so we're losing more, and that's why it's getting cool like it is now. Pretty cool, right? Cool, like, okay, anyway. Hopefully this has helped you enough to figure out, gee, I can plug into my equations. So again, the equations that we have potential energy is equal to mass times gravity times height. We have kinetic energy is equal to mass times velocity squared over 2. We have work is equal to force times distance that we learned before. And we have that equation that if I lose potential, I either gained kinetic or I did work. If I did work, I either changed my kinetic or I changed my potential. If I lose kinetic, I gain potential or I did work. So if we look at something like a roller coaster, if you go up to San Antonio and you're riding on the steel eel, you will notice that the first hill has to be the highest. Because if I started off with a low hill and tried to go, if my first hill was only this big and then I tried to go up to a big hill, this would never work because I let you go right here. If I let you go right here, you're only going to go up to the same height. Otherwise, I'd be getting magic energy from nowhere if I could end up higher than when I started. So that's not going to work. So it's just going to go up to here and then rock back and forth, and nobody's going to go on your ride because it sucked. But on the other hand, if you start off way high and you're at the highest point, then I get lower and lower, just like the golf ball. As we drop it, it gets lower and lower because some of that energy is turning into heat and sound. But how did I get up here in the first place? A little engine grabbed onto my cart and went click, 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 all the way up the hill. So work was being done here. Since I did work, I increased the potential energy. All that potential as it falls, I got faster and faster and faster. So down here, I'm rocking and rolling, and I have all this kinetic energy. But then I cruise up to the next hill, and it turns back into potential. And then it cruises back down into kinetic. The only time we add energy, the only part we did added energy was at the beginning when we did work. Once we did work at the beginning, we didn't add energy anymore from that point. And that's pretty much the way it works. So you want to do problem C. Not problems B, we're skipping section B entirely. So go ahead and do problem C, and you should be able to work that out.